Hi students, in this lecture I am going to discuss problems based on angular momentum. Let us see first one. Let's see the question given. A small mass M is attached to a massless string whose other end is fixed at P as shown in the figure. The mass is undergoing circular motion with xy plane with the center, in the xy plane with the center at O and a constant angular speed omega. If the angular momentum of the system calculated about O and P are denoted by L0 and LP respectively, then right, we have to see options like changing, not changing. Okay, let us see how to start the problem. Let first make the given diagram. The diagram is, it is now circle, and given that this is origin and this is now z axis, and given that small mass attached to massless string whose other end is fixed at point P. Let us take now string is, let us say this is a point P, given string is massless. This is now point mass which is following now circular path and omega given constant, right? Its mass is m. So coming to options, L0 and LP do not vary with time. Let us first focus how to get LP and L0. Okay. According to diagram, when we see from the top, it is now moving, it is moving anti-clockwise. When we see from the top, okay. Let us take, this is x-axis and this as given z-axis. That means y is into the board. Y is into the board. Let us take the string makes angle theta with z-axis. With z-axis. Let us take at one instant. This is now location of the point. And velocity is into the board. Okay. Then see how to calculate now angular momentum. Angular momentum about P is equal to R bar. Suppose now this length equal to R. Okay, capital R. Sorry, small r. Then see what I can write here. R bar. R cos theta minus k cap. R sin theta I cap. So I'm writing here. R sin theta. R sin theta I cap minus R cos theta k cap. Right? You can see here. R cos theta minus I cap. Sorry, minus k cap. R sin theta I cap. R bar cross P bar. P bar is m into velocity. It is now at this instant, velocity is now into the plane of the board. That is Vj cap. Now see calculation. We can take M, V are outside. M, V are outside. Remaining is now I cap cross J cap. That is K cap. Sine theta K cap. Next. K cap cross J cap. K cap cross J cap means minus I cap. Minus of minus plus. So plus cos theta I cap. Okay. That means now angular momentum about P. It has two components. One is along z axis and one is along x axis. Okay. Next. And you can see here he's asking, are they changing or not changing? Now see here what we can do. If you want to calculate about center of circle, see what is the value of theta. If you take point P is at origin, then theta becomes 90, right? Just take this point 2 at O, then theta becomes how much? It is 90. Okay, that means sine 90. Sine 90 is 1, cos 90 is 0. That means if you take about center of the circle, it becomes MV, then this R becomes radius of the circle. Let us take it as capital R. Okay. And M into V into R into K cap. And you can see here M is a constant, V constant, R constant, K cap also constant. That means if we are taking angular momentum about center of the circle, then its magnitude as well as direction both are constants. Means it does not change with the time. Okay. But if you are taking about P, or you can say about any point on z axis except center of circle. It is having two components. One is along z axis and one is normal to z axis. Students, we have to keep in mind this is a component at this instant. Okay. This direction is not a constant. Okay. That means coming to about any point other than this origin means other than center of circle remaining about any point on z axis. This value is changing. That means I can say here modulus of L bar P is a constant. That is what we can say directly by seeing that expression, right? If you take modulus of this is how much? 1. So M into V into R, this is a constant. So modulus value is not changing. Okay. Modulus value is not changing. The only thing is it has two components. One is along the axis of rotation, other is normal to axis of rotation. The component along the axis of rotation is a constant, but the component normal to axis of rotation is keep on changing direction part, not value. Only direction part changing. Okay. That means, and one more thing you have to observe here. See here what we can write this value. M in the place of V, R omega, and R is there. So M R square omega. This is equal to I into omega because M R square is moment of inertia of the particle about O, right? I omega. And in this case, direction of L bar and direction of omega bar both are same. So we are knowing that in circular motion, direction of omega bar is along the axis of rotation. And here, when we take L bar about center of circle, direction is along the axis of rotation. That means when you are taking about center of circle, we can write, we can write, we can write It is L naught bar equal to I into omega bar. Okay. Direction also match. But if you are taking any other point, then what happens is, I am showing here, what happens is, it has two components. It has two components. One is along the axis of rotation. One is along the axis of rotation. Other one normal to axis of rotation. This is now resultant of those two components. This is L bar and this direction of omega bar is Z axis. Okay, but L bar is now like this. So direction of L bar, direction of omega bar, both are not matching. Okay. Only thing is that the Z component, you can see here MVR into sine theta. See what I can write here. Z component of angular momentum is constant m into v into r sine theta, which is equal to radius of circle m into v into r. Okay, so this value is a constant, but the normal component is keep on changing its direction. What happens here? Normal component magnitude does not change, but its direction keep on changing. That means L bar vector is keep on rotating about axis of rotation. Means its modulus value not changing, but direction changing. Okay. And here one more conclusion we can draw, that is component of L bar along the axis of rotation remains the same as long as the point is on the axis of rotation. I am repeating, component of L bar along axis of rotation does not change as long as the point is on the axis of rotation. That is m into v into r. That means I can write here this Z component as I into omega, Z component. This is only component, okay, not vector. But here it is L bar equal to I omega bar. Okay. These points we have to keep in mind. That means when you are taking about center of circle, L bar vector does not change, both modulus and direction. If you take any other point, modulus value does not change, but direction keep on changes. Okay. And next conclusion is like when you are taking about center, then direction of L bar, direction of omega bar both are same. Okay. Remaining points, modulus value not changing, but direction keep on changing. Okay. And final conclusion is that component of L bar along axis of rotation does not change as long as the point is on the axis of rotation. Okay. Now see the options which are correct. L naught LP do not vary with time. That is wrong because LP value change. L naught varies. LP remains a constant. That is wrong. L naught remains a constant while LP varies with time. Option C is correct one. Okay. Now we can see again same problem. More simplified one, more easy one compared to the previous one. A bob of mass m attached to an inextensible string of length L is suspended from a vertical support. The bob rotates in a horizontal circle with an angular speed omega radian per second above the vertical, above the point of suspension. So again, same question, no change in that. Angular momentum is conserved. Just now we have seen L bar vector is rotating. Its modulus value not changing, direction changing. So first option is not correct. Second, angular momentum changes in magnitude. That is wrong. Changes in direction but not in magnitude. Yes, option C is correct one. And option 4 changes both in direction and magnitude. That is not correct. So only correct one is C. Means same question asked two times, right? One is in 2012 and second time in 14. Same question. Let us see next one. The position vector r bar given as a function of time, alpha, beta, mass given at t equal to 1 second. Which of the following statements are true about the particle? So asked in 2016 advance. Let us see. Right, first note down the given data. See what is the data given. First of all, R bar as a function of time is given as alpha t cube. And alpha given 10 by 3. So I'm taking directly here only. Alpha t cube, alpha 10 by 3. 10 by 3 t cube. I cap plus beta t square. Beta value 5. So 5t square j cap. Mass given 0.1 kg. At t equal to 1 second, we have to verify all options. T equal to 1 second. Ask like velocity, angular momentum, force, and torque. Right. Directly we can say velocity vector as a function of time. Differentiate this t cube. 3t square at 3 gets cancelled. 10t square. Okay. It is 10t square plus derivative of t square. It is 2t. 2 5 10. 10t. This is I cap and this is j cap. And asking when t equal to 1 second, right? T equal to 1 second means 10 I cap, 10 j cap. Okay, directly. Next, he's asking force. It is actually net force, okay? When you differentiate velocity vector, we are going to get acceleration vector as a function of time. See how much? 20 t I cap plus 10 j cap. And if you take in this t value 1, 20 I cap plus 10 j cap, right? Now force vector, it is given by as a function of time. This is actually net force, okay? Because net force equal to mass into acceleration and mass is 0.1. 0.1 means 2t I cap plus j cap, okay? Right, let us see options given. First option velocity. So take here t value 1, 10 I cap and 10 j cap. So option 1, it is okay. Next, angular momentum with respect to origin. Calculate now. Angular momentum r bar cross p bar. See what is r bar? We have to take when t equal to 1 second. Okay. 10 by 3 I cap. 10 by 3 I cap plus t equal to 1. 5 j cap. That is r bar. R bar cross p bar. P bar. Velocity 10 I cap plus 10 j cap into 0.1. It becomes now. So what it happens? Velocity 10 I cap 10 j cap into 0.1. It is I cap plus j cap. That is momentum vector. Okay. 10 I cap, 10 j cap into 0.1. Right. Now see I cap cross I cap 0. I cap cross j cap, k cap 10 by 3 k cap. Next j cap cross I cap minus k cap minus 5 k cap. This is how much? 3 5 is 15 minus 15 plus 10 minus 5 minus 5 by 3 k cap. Okay. So angular momentum, how much? Minus 5 by 3 k cap. Okay. Units are Newton meter per second. Right. That is angular momentum. Right. Next. See next one. Next, coming to option C, force F bar is given by when you are taking T value 1, it is 2 I cap plus J cap. That option is not matched, right? Okay, next focus on torque. Torque equal to, say torque equal to what we can write? Torque equal to what we can write? Torque equal to R bar cross F bar when T equal to 1 second. R bar means taking T value 1 here. It is a 10 by 3, 10 by 3 I cap plus 5 J cap cross F bar when T equal to 1, 2 I cap plus J cap. Then see now, I cap cross I cap 0, I cap cross J cap, K cap 10 by 3 K cap 5 J cap cross 2 I cap, J cap cross I cap minus K cap minus 5 to 10, 10 K cap. This is now minus 30 plus 10 minus 20 minus 20 by 3 k cap. Okay, right. So that means option 4, it is matching, right? That means option D correct, A correct, and B also correct. A, B, and D. Let me cross check once units of this angular momentum. So is it correct? Angular momentum, what we're writing? M into V into R, right? M into V into R. Then see what we get. This is a momentum, right? Momentum. Or if you take F equal to dP by dt. So momentum means Newton second, right? dP by dt. Newton second, Newton second, and this is our meter. Newton second meter, right? Newton second. Cross check once. I'm taking net torque equal net force equal to dP bar by dt. For momentum, force is Newton. This is second. Newton second. That is momentum. R is there. That is meter. Newton second meter. Okay. Units. Right. Okay. It is simply calculating V bar, A bar, F bar. Then directly R bar cross P bar, R bar cross F bar. Okay.